My dear students, this is Mona Bhatia welcoming you to Learners Academy. In this lecture, we are going to cover free fall, difference between mass and weight, and difference between your universal gravitational constant and acceleration due to gravity. Plus, we are going to learn how to calculate velocity and time taken for free fall. And along with that, we are going to cover Galileo's experiment on free fall. So stay focused throughout the session. Let's move on to the chapter now. Do you know what is a free fall? Free fall is a state. For example, the moon and the artificial satellite that are moving around Earth, they are all under the influence of gravitational force of the Earth. They are all in a state of free fall. I ask you a question: when you are holding something in your hand, which forces are acting on that object? And once you release that object from your hand, what are the forces that are acting on that object? See, say you are holding a ball in your hand. Now this ball is at rest, and the ball is at rest because you are holding it. You are holding it, and that object, that ball, is experiencing the force of gravitation also, but it is being balanced by equal and opposite force that you are applying on it to keep it there. So now if I say you are holding a pencil in your hand and you are just releasing it, all right? Now once you release the pencil, there is one force that is acting on it, and that is the gravitational force of the Earth, all right? Because you are right now applying zero, you are not holding it, so this force, the force that you were holding it, is now zero. So the outcome is that the force of gravity is more here, so it falls under its influence and the pencil starts to fall down. Now this pencil is in a state of free fall. This pencil is in a state of free fall, all right? Now in the free fall, what happens? The initial velocity is always zero. Initial velocity is always zero, and it goes on increasing. It goes on increasing as it reaches the Earth due to acceleration due to gravity, all right? Now during free fall, the frictional force and the buoyant force, they act on the object. So what are the forces now during a free fall? Which are the forces which are acting opposite the fall? They are frictional forces, force of friction, plus buoyant force. They act against, but they have too less to keep them there, all right? They can only decrease the speed, but to a very small extent. Now free fall is only possible in vacuum, all right? How do we calculate velocity and time taken in case of a free fall? Let's have a recap of all the points that we have learnt in the previous slides. The first says, in a free fall, initial velocity of the object is always zero. That means u is always zero, and it goes on increasing due to acceleration due to gravity of the Earth. Second point, during free fall, the frictional force due to the air opposes the motion, and buoyant force also acts on the object and it opposes the free fall. Third point that you have to keep in your mind is free fall is always possible in vacuum, all right? Now to get the Newton's equation of motion, kinematic equation for motion, for a free fall, we always take u is equal to 0 and acceleration will be equal to acceleration due to gravity. Okay, so now Newton's equation for motion can be written as v is equal to gt. Why do we write v is equal to gt? Because earlier we had V is equal to U plus AT. Now here, since this is 0, so what, and here A is always G, so we'll write G over here. So what do we get? V is equal to GT. Alright, the second is S is equal to half GT square. So why do we take this? Because S is equal to, the actual formula was S is equal to UT plus half GT square. Now since we have this Z, this is initial velocity is 0, so this multiplied by T will also become 0 plus half G, sorry, just excuse me. Alright, so okay, so what do we get? Half GT square. So this comes out to be half GT square. Alright, now the third kinematic equation is V square is equal to, you remember that? What is the third kinematic equation? V square is equal to U square plus 2AS. Alright, so when we fill the value, because initial velocity is right now 0, so plus 2A, A is actually G. Alright, so I'm going to do it in the next step because I forgot to do. So this comes out to be 2GS. Alright, so V is equal to under root 2GS, or you can say V square is 2GS. This is how, these are the kinematic equations, and in case you have you know the time factor, alright, if you know the time factor, then you will use this equation, and if you know the distance, you will use this equation. In case you don't know the final velocity and you want to know about one of these like time and S, so you will use this equation. Alright, what is the reason that feather and stone reach the earth at the same time in vacuum? Because the value of G is same at a given place irrespective of their masses. So when two objects, irrespective of their masses, see here this small ball, it should have a less mass m1, and this is mass 2. So old school of thought, people had old school of thought always believed that the heavier object will reach earth faster before the object which has got light weight, but it was proved by Galileo that this is not correct. So Galileo did one experiment, and both the balls of the different masses, they reach the earth at the same time. So this was proved by Galileo. So what is the reason? Because the G, value of G is same at the same place irrespective of their masses. Galileo dropped two spheres of different masses from Leaning Tower of Pisa, and he successfully demonstrated that both the sphere reached the ground at the same time. But this is not true. This is not the case with feather. This doesn't happen. But why? Because the feather experiences buoyant force and also a frictional force due to air, and therefore what happened? It reaches the ground very slowly. But in case of a vacuum, this will not be possible. In case of a vacuum, you will find that all the object will reach the ground at the same time. In vacuum, they will take the same time, and this experiment has been scientifically proved now. Alright, now what is the difference between mass and weight? in our day-to-day life we use the word weight for both mass as well as for weight. Say for example, if there is an object which has got a weight of, when we say it has got a weight of 10 kg, what we actually mean is the mass of the object. Okay, that is the mass that we have calculated. So our weighing machines, they actually tells us the mass. Now if we have to calculate the weight of the same object, we will have to multiply it with the g. So mass is 10, when we multiply it with 9.8 we get 98, and that will be the actually weight of that object. All right, now I'm giving you all the list of differences between mass and weight. The first is mass is the amount of matter present in the object. Second point that you have to understand is the SI unit of mass is kg. Third point is mass is a scalar quantity. That means it does not have any direction. All right, it has only magnitude. Mass of an object can never be zero, and mass remains same everywhere. Value of mass does not change even when we go to another planet. Okay, so now opposite to all these points, I'm going to highlight the difference. Like these are the points for mass. So what is the difference? Now I'm going to tell you about weight. Weight is the force with which Earth attracts the object. And what was mass? Mass was the amount of matter present in the object. Now SI unit of mass was kg, but the SI unit for weight will be Newton. Okay, mass is a scalar quantity whereas weight is a vector quantity. It has direction as well as magnitude, and weight of an object becomes 0 at the center of the Earth. All right, now weight of an object changes from place to place as the value of g is not same everywhere. All right, see what is the difference between g and small g, that is universal gravitational constant and the acceleration due to gravity. All right, the first point, that capital G, that is universal gravitational constant. Okay, universal gravitational constant numerically equals the force of attraction between two unit masses kept at a distance from each other. Okay, kept at a unit distance from each other. Third point is that capital G, that is universal gravitational constant, is a scalar quantity, and next is its value is constant throughout the universe because it is a constant value. All right, it is not going to change because of any other external forces. Now the value of G is calculated is 6.67 into 10 to the power minus 11 Newton meter square per kg square. All right, the SI unit of universal gravitational constant is already given in the previous point, but I'm again writing it for you, Newton meter per square per kg square. Okay, now we have to now give a contrast to this. So acceleration due to gravity is the small g, and what is it? It is the acceleration produced in a body under the influence of gravitational force of the Earth. All right, now this is a vector quantity. Acceleration due to gravity is a vector quantity. It has a direction as well as magnitude. The value of small g, that is acceleration due to gravity, it varies with depth and height and also with the shape of the Earth. Now on Earth's surface the value of g has been calculated and it is equal to 9.8 meter per second square. All right, SI unit of g is meter per second square. I hope you enjoyed watching this video and learned the concept very well. I'm going to cover many more interesting topics in the coming videos, so stay tuned. If you have any question, email us at learnersacademy.classes@gmail.com. Till then, keep learning, be healthy, be focused. All the best. Bye bye.